Let's talk about a slightly different problem today, but defects never fear. Defects will make their appearance. So, so this is a more of a shape problem I'd like to discuss today. In particular, we saw William Irwin's lectures, interesting topological structures made from really soft things, fluids. Today I would like to show you, try to convince you that you can get really kind of sharp structures, faceted structures, normally reminiscent of hard materials like gemstones. How you can get those from very soft objects. I'm going to be talking about a fluid. Well, it's actually a thin shell, and it's actually going to be a liquid crystal. But you know, liquid crystals flow. All these experts here, you can get it in a container, and you can pour it out. So I would like to, this is an image of a symmetric liquid crystal in bulk. It has all these beautiful patterns determined actually by the defects that it can make, but it pours out, it flows. You can use these things to make 2D thin shell liquid crystalline vesicles, and in some limits, I want to convince you, that can make a sharp object like this. So the star of our show is going to be the simplest kind of polyhedron that you encounter, kindergarten more or less, which is this tetrahedron. All the faces are the same, but the vertices are all distinct. There's no vertex opposite any other vertex in this tetrahedron. 4 vertices, 4 faces, and they do occur in nature. This is a tetrahedral speleothem from Hong Rock Cave in France, the Jordan. If you look there, there's tetrahedral crystallites. But that's very hard. It's also kind of inspiration sometimes in art. This is a project from an architectural firm in San Diego, how to redesign downtown and use some buildings. Well, this is a complex of condominium. And each condominium or apartment is a tetrahedron. It did not win the competition. Damn. You should have. So this is kind of how shapes can emerge. It appears in morphology, for example. It's important to development of biological structures and things like that. There are lots of cool shapes that occur also in soft matter by virtue of the system being easily deformable, something I discussed in my very first lecture here, telling you some of the themes that occur in soft matter. This is a viral capsid, been mentioned several times in these series of lectures, and you can see it facets, particularly when it gets big enough. The small ones, well, these are made of proteins that make a shell, and then DNA is pumped inside these viruses to basically protect it. When they're small, they're kind of round, but when they're large, they facet. This is an elastic-like object. By the way, this is the adenovirus. So this is again one of these viral capsids, and this is an example of biological functionalization. So here are the 12 bifold defects Greg was discussing yesterday. And each of those has a fibril attached to it, and that fibril is used by the adenovirus to latch onto cells that it's protecting. So here's an example of biological functionalization of the defects. They're pentons, they're called for a viral capsid. It's a pentagon on the dual lattice. Each one is marked here by this fibril. So the special role of defects is biologically recognized. This is a nice experiment from 2001 by Monique Dubois' group in Paris. They used surfactants. These are charged surfactants. So you have a mixture of opposite sign surfactants, and they self-assemble, here's an image here, into icosahedra. But again, this is a kind of elastic object. This is also interesting in that where the 5s are, the system spontaneously punctures. So instead of forming a true defect there, it drills a hole in there. So you actually have 12 holes. So this is a sphere with 12 holes, no handles, but 12 holes, which changes the Euler characteristic of the system to -10 instead of 2. So there's holes, things can get inside and outside through these holes. You can take elastic membranes and use 2 components, hard and soft. This is with the Vesicles connecting Monaco Vertigo Cruz a few years ago. So this where the system is hard, it sort of likes to be flat. There's an elastic membrane, 2-component elastic membrane. A lot of richness, also something I talked a bit about in my very first lecture. A lot of richness in these systems comes from the frustration of having more than one component. So here's hard and soft. It likes to stay flat where it's hard. This is hard to bending, and bend where it's softer to bending along these blue edges. And by varying the relative stiffnesses and the relative percentages of components, you can get buckled objects. But again, elastic. And then Robin Salinger and her talked about pneumatic glasses and pneumatic elastomers, and you can engineer defects in these systems to make interesting shapes. It's not what I'm going to talk about. I'm going to talk about vesicles. So we've seen a number of talks where vesicles played a role, and Christina's at his last talk yesterday, there were vesicles with these microtubules that went to the surface, and you had an active pneumatic. I'm going to talk about a passive pneumatic. So a vesicle is a molecularly thin sac. It's a microscopic sac that's molecularly thin. The membrane is, nanometers in size. So we'll be able to treat it as basically a 2-dimensional object. The most important examples are amphiphilic bilayers. So here you use lipids, basic composition of the plasma membrane, basically every cell in our body. So the structures there are called liposomes. I'm going to talk about polymer realization today. So the basic amplifiers in these systems are going to be block copolymers. And they have a little bit more robust, but they do similar things to these liposomes. But the structures that can make polymerisms. Now, when you use block copolymers, one of the cool things you can do is to build in liquid crystalline functionality to the system. So I'm going to be talking about a block copolymer. So it's basically a coil rod system, covalently linked. That's what block copolymers do. So you have this coil as a peg, so it's sort of hydrophilic. It's analogous to the polar head for the lipid. And then you have a hydrophobic tail shown in black here. But synthetic chemists have been able to attach nematogens to, for example, this rod-like backbone here. So now you have, so this is a biofilament. It's a decorated biofilament. Now, so this is what it looks like here. Here's this cholesterol-like thing. That's the mesogen. Now, if you're really clever, you take a 3D liquid crystal former, make it these side chains, incorporate it so that as an amplifier, this object will make bilayers and make the polymer zones that I described before. If you're lucky and clever, you can translate the liquid crystalline order of the bulk liquid crystal former here into liquid crystal order in the thin shell itself. So this makes a 2D liquid crystalline polymer zone. So here's one example. So this came up with a collaboration I had with the group of men who lead the Curie Institute in Paris. This is the mesogen that they use. This is what it looks like in the bulk. Okay? So it makes a smectic in the bulk, a layered structure here. It's a special kind of smectic. You can see, here's the phase diagram here, and it's got a little D here, which stands for, it's a little bit hard to read. This is a small D here, which stands for interdigitated phase. So the mesogens coming down one backbone here and down another backbone here, and they sort of interdigitate like that, and then make stripes. So the stripes are the smectic structure. These are the mesogens that are linking this way to enable that smectic order, and the layer spacing is around 4 nanometers. So for the bulk object, nothing about vesicles yet. Here's phase diagram from calorimetry. So it goes from isotropic directly to the smectic phase. And then there's low temperature glass. By changing the mesogen, you can make intermediate pneumatic phase, so isotropic to pneumatic to smectic. So I'll discuss cases of both pneumatic and smectic. So here's this cartoon of this structure assembled into a vesicle. Here's the bilayer, and this interdigitation occurs, then it extends through the 2D shell. So there's some remarkable symmetry breaking here, which is not, I would say, 100% understood. I've worked on it some, but for now we're just going to assume that this happens. And here they make giant unilamellar vesicles. Lena was discussing these objects. So if you look carefully here, I'm not sure if you can see them, this is stripes. Here's the unilamellar vesicle, here's the membrane, and across it, it's striped. This is the big object. This is now smectic order in the 2D membrane. Vesicle. And this layer spacing is the same, the same as the spacing in the bulk. So we have now a liquid crystalline vesicle. And the question I want to ask is, what is the shape of this object? So the experimenters studied this and put this on an electron microscope grid, and one of the things they saw was fairly sharp objects. In some cases, faceted-like objects. The vesicle is here. This one is just ice underneath. Okay, so with Sean Jing and Henry Mao and Horman Chin, two of them studied this problem analytically, and we did some numerics to describe at the end. So, what is interesting about this problem? You have two sort of things that you have to minimize. Okay? Let's imagine first that we have just a monolayer like this. then I'll look at the shell and spherical topology. We have a monolayer. We have an integral over some surface to be determined because the thing can bend. And it's ordering. So it wants to form, say, a pneumatic or a symmetric, and it's free as a membrane to deform in space. So when we compute the liquid crystalline free energies of this system, we have, splay and bend that we've been discussing, two-dimensional system, so there's no twist. But the gradients that appear there are on a curved surface to be determined. So the ordering is dependent on the geometry, and the system is simultaneously bent in space and has some curvature, and you're integrating over a surface that's determined. But the surface changes the liquid crystalline free energy and the bending energy, and the bending energy can change the preferred surface. So you have a kind of a doubly infinite dimensional problem. So you've seen Jonathan Salinger went in detail through mean field theory, the Landau-Dijen theory, for determining that you could get some kind of ordering transition with this orientable order. Now you allow this to occur on a manifold to be determined. Tremendously challenging problem in general. And also tremendously difficult computationally. So imagine you simulate this liquid crystal now, and then you do it on some lattice, but you don't know what lattice to do it on. So you have to update all the orientations of the molecules, like updating all the spins, and then update the surface, and then that changes the liquid crystalline energy, and then that changes the preferred surface, and so on. There aren't even good computational methods for these kinds of problems. Certainly not fast ones, and ones where you have, global moves like Swenson, Wang, and spin systems, and so on. Okay, now, what are we going to tackle analytically? In general, as I said, there'll be two Frank constants for the liquid crystal, splay and bend. In general, there can be some spontaneous mean curvature for the system. So this is this average of the radii curvature, inverse radii curvature that you've seen several times. And it might have a preferred spontaneous value, H0. So this is actually a vector if you have a membrane, but there can be three components for the spontaneous curvature. So that gives you 3 plus 2 is 5 components, and then the bending rigidity can be anisotropic. In general, that will have 3 components, so sort of 2 parallel and perpendicular ones. I'm going to simplify that. I'm going to take one Frank constant, one bending rigidity, and we're going to, in the end, we're going to put this together and take a symmetrical bilayer, so there'll be no spontaneous curvature. So I'm going to reduce this down to a 2-parameter system. Now, this one Frank constant approximation can be of 2 different kinds. So if we take, so remember, in 2 dimensions, displays the divergence of n. The bend, which is n cross curl of n, in 2 dimensions is just curl of n squared. If we take these two to be equal, k1 equals k3 equals k, this just sums up into d of n all squared. K times d of n squared. This is called a nonlinear sigma model by the field theorists. There's another limit we can treat simultaneously. We can take the limit that n that bend is completely suppressed. So let's take K3 to infinity. No bend, just pure splay. And get rid of this term. That's an interesting system, and in fact, remember N is a unit director, so it has one constraint on two components, that leaves one free component. If you simultaneously require, K3 goes to infinity means the curl should vanish. If you add this constraint, so this is epsilon I, j, d, I, n, j is 0, n is completely determined. And in fact, you can prove from this condition that n dot gradient of n is 0. That means n is conserved along itself. So this means it forms a geodesic, completely determined so-called integral curve. So if we do that, this limit, we just have pure splay. If we have pure splay, in terms of n, we can construct the orthogonal set of curves, and that's a constant layer spacing object. So that describes a symmetric. So in that case, K3 goes to infinity here. K, my single component will just be K1, and it will couple to curl, to divergence, and I construct the orthogonal curves, and that describes the symmetric layers. So it will be perfectly equally spaced layers. So I'm not allowing any compression of the symmetric. So I've integrated out the symmetric completely. So I'll be simultaneously treating those two cases. I'll mostly describe it for pedagogical purposes. I'll mostly talk about the symmetric because it's easiest to imagine. So now you have this, you want to put constant layer spacing lines on the surface to be determined to minimize free energy. Okay. Minimizing the free energy means that that n should be constant. Yeah. But remember, the gradients that appear are curved gradients. The covariant derivative of n to be 0. So any time you have some inhomogeneity in the director field, that's going to cost you energy. And any time you have some curvature, that's going to cost you energy. Because this D will not only have a regular gradient, but it will have connection contributions. So that means you want to minimize this. You want something where the Gaussian curvature vanishes. This is called a developable surface. So it's something you can build from flat space, plane, cylinder, cone, and just fold it up, wrap it up. And then minimizing the bending energy in this case, from a developable surface, you want H to equal H0 to minimize this. And so this will give you a cylindrical monolayer. So this is basically a nanofiber. And the radius will be 1 over the spontaneous curvature. I don't want to do that, I want to look at bilayers, like we have for liposomes, to make these polymers up. So I'll take 2 copies of this monolayer free energy. And I'll take it symmetric. There are 2 possibilities for this. You could, of course, just have a flat monolayer, like this table here. But that object has an edge, has a boundary. This free energy is scale invariant. So this part here doesn't change, and nor this part if you scale the system up. But if you have an edge, that does change. The perimeter changes. So for a planar system, there's a line tension at the edge, and that energy will grow with the system size. So this was shown way back in the 70s by Helfrich in 1974. The same brilliant line physicist who invented twisted pneumatic displays. the system will spontaneously get rid of boundaries when it's big enough. It's the large cost of the perimeter line energy. So it likes to spontaneously close up. So this is a topological feature. This spontaneous topology change to eliminate holes. So then we have a closed vesicle. Yeah.
I missed the point where you said about missing the preferred action.
Yes. So if I take two copies now like this, and I treat each layer symmetrically, then there's no preferred bending like that. If you have sort of cone-shaped lipids or polymers, block of polymers or something like that, you can have an asymmetry between the outer and the inner leaflet, and that'll give you some spontaneous curvature. I'm going to take the symmetrical case. So there's a layer, midsection in between, and above and below are the same. In that case, H0 by symmetry has to be 0. That's to simplify the problem. So this gives us now, if we close up the hole, we have something with spherical topology, and we're only interested in the shape. Okay, so I have a closed bilayer polymer vesicles. Now, I said it wanted to be flat, right? It doesn't want to have any Gaussian curvature because that contributes to covariance derivatives. But now this is frustrated by the topology. As you've seen many times now, we have Gauss-Bonnet theorem relates the local curvature integrated up to a global topological invariant. I discussed this also in my lecture, the Euler character. It's 2π times the Euler characteristic, which is 2 for the sphere. So this is 4π. It's big, it's not 0. It's far from 0. It's 10, 12. So the system cannot be flat. Wants to be flat, but it cannot be. So the liquid crystal free energy competes with the bending energy in this case. And we want to know what is the shape of this object with spherical topology that minimizes the sum of these free energies. Now there are two important cases. So now I just have the two parameters, the Frank constant K and the bending rigidity K. First one I'll call stiff. This is with respect to bending rigidity. So very high bending rigidity. Doesn't want to deform away from being the sphere. So in that case we have a round sphere and we have all of the physics of a thin shell spherical pneumatic, say, or thin shell spherical cement. That's quite interesting. The liquid crystal order might, for example, if you have a symmetric, it will deform a little bit away from being a sphere. Symmetric has constant layers like that. If you have constant layers, it's easier to bend them along the layers than transverse. If you bend them transverse to the layers, that changes the layer spacing, and that costs symmetric energy. So the system will be a little bit ellipsoidal, easier to bend along than transverse, and make, so it'll make, so it preferentially bend one way along symmetric layers. Some other interesting things happen. We've seen that so the basic defects for the liquid crystal are 1/2 strength objects. So we have to have enough defects to make up the Euler character 2. So we can have 4 1/2s, 2 +1s, or a +1 and 2 1/2s. So here's an example of this kind of object for the block copolymer system. And in the symmetric limit, one thing that's interesting is that instead of the 4 defects being equally spaced at the vertices of the tetrahedron, you can show that they prefer to live along a great circle. And the reason is a +1 defect is, unlike the case of the one Frank constant case, +1 defect is degenerate with 2 1/2s. So you can take a +1 like that, and then you can rotate it. Remember I said the director for the symmetric is basically an integral curve or a geodesic. So you can extend it out around the system, cut it along a great circle, and this plus 1 becomes 2 1/2. And the same for the plus 1 on the bottom. This costs 0 energy. The direct doesn't change anywhere in this deformation except at the defects. So this produces 4 1/2 defects with an arbitrary aspect ratio along a great circle. Amusingly, this planar configuration is the one that occurred in the biological clock that Christina described yesterday. Where in the active system it goes from tetrahedron through a planar structure to an inverted tetrahedron and back. This planar arrangement of defects occurs in the symmetric limit. Zero mode. Anyway, there's quite a bit of fun physics. You can make these thin-shell pneumatics, and the precise position of the defects depends on K1 over K3 and so on. So people have studied that quite a bit. But the more interesting limit is the other one, I call the floppy limit. We'll come back to this. This is, well, you've seen all this before now. Defects for various symmetry objects. But I will come back to that. Let's look at this other limit. It's a floppy limit. So this is the limit where it's easier for the system to bend than it is to undergo liquid crystal deformations. So if we have two terms in the free energy, the bending term and this liquid crystalline term, and one has a much bigger coupling constant, that's going to dominate the free energy. You can even take the limit where the bending rigidity is 0. So the system can bend however the heck it wants. And we want to minimize this frank free energy, but with the constraint that it's topologically a sphere. So this is the problem that's at hand, minimizing this frank free energy with non-vanishing integrated Gaussian curvature. So the solution is fairly obvious actually. You want it to be flat over as much of the surface as possible. So that you can do with facets. You have flat faces and then some edges that separate them. So from a two-dimensional point of view, if you have something faceted, it's flat everywhere except on edges, which have only one dimension, basically vanishing area for the membrane, and at the vertices, which are point-like. So you can solve this problem by faceting. Faceted object is almost everywhere flat. This is funny. We've said we've made it floppy. When it's floppy, it flattens. This is weird. This is really weird. But it's quite simple, really. And on each face, it's obvious. You can make parallel lines, straight rows, uniform spacing. That costs 0 liquid crystalline energy. You can make the liquid crystalline energy 0. So we don't have to do too much to prove this is the exact ground state of the system. Now, how many faces? Well, it's better to look at the defects or the vertices. This is where the defects come in to save us. Somewhere, you can think of the defects either from the liquid crystalline point of view or from the geometrical point of view. If it's flat everywhere, but the integrated Gaussian curvature is 4 pi, we have to have some delta function sources of curvature. Those will go at the vertices, and the vertices can simultaneously be liquid crystalline defects. To specify a surface in 3 dimensions, you need 4 points. Otherwise, if you have 3, they could just be collinear and coplanar. So you need 4 points. So the possible sets of defects you could have, I said you could have 2 plus 1s, that only gives you 2 points. That will not specify the object in 3 dimensions. You can't have a plus 1 and 2 1/2 because that only gives you 3, which can be coplanar. So you need the full 4 1/2 defects. So we'll have 4 points. They span a non-degenerate polyhedra. And we can have ground state shape then. So we have 4 vertices over the faceted objects that give you a tetrahedron. So how does it work? It's very easy to do. You can just draw it in flat space. So you've all, I would have done something like this. Take a tetrahedron, 4 faces in the plane, and fold it up by bending. So this is origami. Bend along these edges. Then identify. You get this. Draw parallel lines on the plane. Easy to do. When you fold it up, they continuously connect. Everything's fine. Hunky-dory. You have perfect symmetric on the tetrahedron. Nothing funny except for bend happens across the edge, but the bending energy is very, very small, maybe 0. So that's fine. What about the vertices? That's where the curvature is, but that's where your plus 1/2 defects are as well. Come along here, go around 180 degrees. Same. So those are your 4 1/2 disclinations. Now, in general, how many, what kind of space are we working in here? How many ground states can we have? So we discussed this also in my lectures on topological defects. We have a manifold of ground states and some interesting topology and so on. How many ground states can we have in this case? So a tetrahedron has 4 vertices in 3 dimensions. How many parameters does that require? 4 vertices in 3 dimensions. Wakey, wakey. Coffee's coming. Come on. You can't get coffee till we answer this. Each vertex has 3 coordinates. So, come on, go for it. Huh? 12. Yes. 12. 4 vertices, 3 coordinates. So that's 12 coordinates to specify the tetrahedron. We're interested in shape. So we can rotate it and we can translate it. That doesn't change the shape. So how many does that get rid of? How many rotations do we have? 3. Translations? 3. So that gets rid of 6. That leaves us 6 coordinates, 6 numbers to specify the tetrahedron. We can also scale. Okay? Holography. Scaling up and down. We don't care about the overall size. So that leaves 5 parameters to describe this tetrahedron. But also it had to be built from flat space. So when you put this down in flat space, the sum of the angles around one of these objects is 180 degrees. There are 4 of these vertices, but there are actually only 3 constraints from this, because one, you have to do the algebra, one constraint is not independent. So there's 5 dimensions, 5-dimensional space of tetrahedra. For this problem, not an arbitrary one, to build it from flat space like this, it's just a 2-dimensional space of ground states. So that basically is determined by this triangle that you build here. You can have an equilateral triangle, that's one, but you can have a different angle here from here. Varying those 2 angles will vary the kind of tetrahedron that you get. It's a 2-dimensional space of ground states. Here's a symmetric Trojan horse from Syracuse in Barcelona. So you can hear the equal layer spacing objects. It's nicely faceted. There's some boundaries down the bottom. I'm not sure. Okay, so now you can check this idea with simulations. So this Holman did this. So up here shows varying the stiffness. Okay? And this shows, the top shows free energies, bottom shows bending energies. And as you go to the right here, you go more to this floppy limit I described. And these two rows are K1 equals K3. You start to see some faceting. And here is going more towards the smectic limit, where K3 is bigger than K1. And you start to get these very faceted objects. And they depart quite a lot from being spherical in shape. So you can compare this with experiments. So here's kappa equals 0.04, and K is K1 is 1, so K3 is 2. So this is the floppiest kind of object. Here it looks something like these seen in the experiments. Here's kappa equals 0.1 compared with K1 is 1. Much floppier than it is to form the liquid crystalline energies. You get something, this projection looks like that. And then here, where it's what I call stiff, you can see it's basically spherical, right? And you get something closer to this. Now, you can also have nanotubes in this system. If you have a nanotube, you're going to have some, so that's basically a cylindrical-like object. And the bending is going to be over the whole surface. So if I set the bending rigidity to 0, I get this equilateral triangle. I get this perfect tetrahedron as the ground state, because if I restore, if I restore the bending rigidity, I have a bending energy which is the sum of the lengths of the edges, since it's concentrated over edges. So the minimum of that is the tetrahedron that minimizes the sum of the edge lengths. So that's the regular tetrahedron. So the bending energy is proportional to the square root of the area, the length of edges. The nanotube is bending across the whole surface. So that has bending energy that goes as area. So for large area systems, the square root wins. You favor a tetrahedron. For small systems, you can also get a nanotube in this system. And there's a crossover length scale which is occur. Now, how about getting other polyhedra? Okay. Well, there's this fairly simple solution. I had 4 basic defects for the pneumatic order, for liquid crystalline order, because I had to make up the oil characteristic 2 from strength 1/2 objects. If I change the kind of order, so that's p-fold, where p is 1 for vector order, p is 2 for pneumatic order, that's the inversion symmetry. So invariance under 2 pi over p. The basic defect has strength 1 over p. P is 2 is 1/2. Vector order, vortices and so on, is p equals 1. So we saw strength 1, vortices and so on. We counted all those in our lectures. So let's look, for example, at tetratic order. So these are objects with 4-fold symmetry. Imagine you have little crosses or something. So you engineer molecules that are crosses like that. And then you make those self-assemble. So in that case, the basic defect is an analog of what Greg described for a crystal. Instead of cutting out the 60-degree pizza wedge, you cut out a 90-degree wedge and identify the edges together. That's a strength 1/4 defect for tetratic order. So if you have strength 1/4 defects and you need to make up 2 and they're all the same, how many do you need? How many 1/4 objects do you need to get? 8. Right? You need 8. So, we're going to have 8 confirmed points in that case, which suggests a cube, right? So in that case, you can just do this kind of construction. So you have square tiling, if you want. Those are your little cross-shaped objects. Square tiling, you do it in flat space. And then you just fold this up, and you get the 6 faces of a cube, 8 vertices. Each vertex here, when you fold this up, loses 90 degrees. Okay? So that when you close it up on a cube like this, you go 90 degrees, 90 degrees, 90 degrees, and come back to yourself. You go around 360 by making 3 90-degree turns. That's the 1/4 disclination defect for a tetrahedron. So, if you could build that kind of object, people like Stefanos Sakana can probably do, that thing should spontaneously fold up into a cube. And then you can do your experiments and shape objects and so on. So that's the way you can get other. So here's some pictures. This is a so-called Portuguese tiling. You can see in Rio de Janeiro, square tiling. This has been studied a little bit by Jonathan again. And here's just a spherical square tiling with a 1/4 defect. So you can see here, you go around, it rotates 90 degrees. Anyway, so that's a kind of open problem, computing energies of defects, solving for the basic defects, so K1 is not equal to K3, finding tetradic free energies and so on is quite complicated. So let me just conclude, so we can have some coffee before Chris's talk. The building blocks here were these rod, coil, block copolymers with liquid crystal side chains. The emergent structure, if you want, was a topologically spherical bilayer vesicle. The material parameters are elastic modulus and a bending rigidity. The stiff limit gives you round, pneumatic or symmetric vesicles. The floppy limit gives you faceted vesicles. So the floppy limit is the one that generates the sharp structures. Thanks. Any questions?
I guess physically, how do you change the order, right? Of the
Okay. So the liquid crystalline case, we need rod-like molecules. So you would have to synthesize cross-shaped objects in 2 axes of symmetry. Or there have been some experiments by Harrison and Paul Chaikin and so on. So they look at disks in an electric field or magnetic field, and they sit up on edge. So when you project down, it has a kind of, so you can imagine objects that break some of the pneumatic symmetry by being sort of rectangular in shape. So those will inherit some tetradic orders. Now you have 2 axes. And those, so the disk on edge projected, it's a bit like the tilt order you project. Tilt you project on the surface, you get a vector. If you just project down, you can get some tetradic order. And those systems, if you measure orientational correlation functions, exhibit some 4-fold symmetry as well as some pneumatic symmetry. First approximation to this is just a line, but then if you recognize it's really rectangular, it will have tetradic order. How they will self-assemble, it is much more complicated now because you have to, there's 2 the thing can rotate like that, and it has to, if you use a cross-shape, then it's not so clear. Or a square. You have square-shaped objects that are similar to tetrad. But there are no really good examples here.
In the experiments, how are you able to change this stiffness parameter?
Yeah, Okay. You can't vary much. So you can vary the relative lengths of the two block copolymers. So it's A to the M, B to the M. And that changes the thickness of the vesicle. And the bending rigidity goes as the thickness cubed. So it varies. And playing with things like that. But you can't, it's really hard to actually calculate them and to map them directly onto the theory and to know exactly what they are. And you can't vary them that much. Otherwise, you lose this delicate 2D liquid crystalline.
Is that dependent on other solvent conditions? Or?
Yes. So it's a tricky system because of being an amphiphile. So when you form it, you have to have something that is a solvent, like dioxane, that's simultaneously sort of hydrophilic and hydrophobic. It has to dissolve both components, and then you dialyze it out, and then it all is, yeah. So there's a lot of kinetic stuff that goes on as well, and it can get trapped in metastable states, kinetically trapped states, and so on. For example, the round ones, some of the, so this one here, this one is actually smectic here, and on here it hasn't yet converted to the smectic, it's isotropic. So this is a little baby universe here sticking out of this membrane, that's isotropic. So it started to order here, and then it gets stopped by this neck, which has a big energy. And it has to either shrink this down to a defect or retain it like this. So what this is basically is a blown up defect. Remember, the core of the defect is isotropic. So you can blow that up like that. So all these kinds of things happen in systems. So it's a lot of kinetic, really interesting things as well as the equilibrium changes. Yeah.
Under what conditions could such a vesicle split into two?
That's a very good question. So one of the brilliant things about this polymer zone is you have all of the liquid crystalline functionality at your disposal. So you have thermotropic response, you have electric and magnetic response, and photo response. So they've actually constructed some of these things so when you blast them with light, for example, they burst and so on. So at least one of those cases is fairly well understood. François Brochard worked on the theory of that. I don't remember all the details. That's and they're a little bit more robust than lipids. So they're actually pretty nice systems. But so people work on that for application as deliverers, drug deliverers and so on, genetic therapy and so on. You get it inside some place you like. It's a fairly innocuous substance. You can get even into nuclei and burst it, deliver it. Cancer drug. Okay, so let's see if this.